Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the online lecture on MATLAB simulations of feedback control systems. Last time we were discussing how to implement integral control using MATLAB, and I will just briefly revise what we did last time. So I will just create, instead of going through the code that we wrote last time, I will just create a new code. So in order to implement the state estimation based integral control, which is the topic of today's lecture, we first have to we start step by step. First we write the function file for the system, as we do function dx equal, let's say, ss model 3, and the input to this function will be time and the state variables x, t comma x, and then you have to write down the system matrices for the system. So this is our system. X dot equal this matrix A times x plus b times u. So let me write down the A and b matrices. For the system, we have the A matrix is equal to 0 1 0 0 0 1, and the last row is -4 3 and -2 -2. So next we have the B matrix. The B matrix is 0 0 1, so it is 0 0 1, and so now we can design the feedback control law for this system, because for full state feedback we have u is equal to minus kx. So we just have to see if this system is controllable and observable. So you can see here in this slide that determinant of the Q matrix is -1, which is non-zero, so the system is controllable, and the determinant of O matrix is equal to +1, which is with the output of x1. Right now we are not talking about the output, because we are just trying to implement the full state feedback for the system. So what we do is we calculate we copy the A and B matrices from here, Control C, and then we paste them here, Control V, press enter. Now A and B matrices are in the command window, have been defined. So I define K is equal to place. Place is the command used to place the eigenvalues of the closed loop system at any desirable locations. But since this is a single input system, I can only have non-repeated eigenvalues. So let's see, if I place the eigenvalues at -2, -4 and -5, then the corresponding control gain is 36, 41 and 9. So I put this gain here. K is equal to 36, 41 and 9, and u is equal to minus k times x, and now we have dx is equal to ax plus bu. So that's our feedback control system with full state feedback. We save this file as ss model 3, and we create a new script file CLC clear all. You can also use the command close all, which closes all the figures that are open before we run this file. So we have t comma x equals ODE 45 at our file SS model 3, and we need to run it for 0 to 15 seconds. Maybe you can choose any. Now we give initial condition for all three state variables. Let's say we give -1, +2, -4, whatever initial conditions you want to give. Okay, so this command will give us the state and the state trajectories, which we can plot using the command t comma x, and we can have the grid on. We can have x label x label as time in seconds, and we can have y label as state variable values, and then we can also have the legend, because we are going to plot three states. So x1, x2 and x3. These are our three states, and you can just run this file and save it as SS model 3 _ s, just to emphasize that this is a script file for SS model 3. We save it, and you can see here that all the three states are asymptotically stable, and there is no problem with asymptotic stability. But suppose we want to track some value. So for example, let's say we have a desirable value for the state vector. Let's say x desired equal let's say we wish to track the state x1 3,300. so we want the x1 to go to 3, and we want the other states too. So this will be minus k times x minus x desired. So we save it, and we see if the reference is being tracked here, and when we run it, you can see here that this does not quite reaches there is a steady state error. So in order to remove that steady state error, we learned last time that we need to use the integral control. And so what we do is we apply the integral control. Just close it here. This is the way you apply integral control. You add a fourth state variable in the system, and then you can basically use that integrator state to remove the steady state error. So this is exactly what we are going to do. Let's see, go back to this system, and we are going to change the A and B matrices, and we have to recompute the gain as well. So in order to add another state, in the first row of A matrix we add a 0, similarly add a 0 in the second row, add a 0 in the third row, and then the final row of the A matrix would be 1 0 0 0, and similarly there will be an extra 0 in the B matrix. The B will become 4 by 4. We copy these A and B, control C, copy these matrix, put control V, place them here, and then I can let's say put another eigenvalue at -1. So now we have 4 states, so we have fourth order closed loop system. So this will be we have to tell MATLAB about the 4 desirable pole locations for the closed loop system. I have selected all 4 poles in the open left half plane, and this is my control gain 74, 52, 10 and 40, and I will implement this gain 74, 52, 10 and 40, and now this is my new gain. And so instead of having x desired equal to the whole state vector, I can simply have y desired here, and u is equal to minus kx, and then we have to change the state space system according to this equation. So we have x dot equal ax plus bu plus this whole vector 0 0 0 minus 1 times y desired. So this we add into here plus this vector 0 0 0 minus 1 times y desired. So this will be this is our integral control. And now since we have 4 state variable, so we have to, in the initial condition, we have to give the initial value of the 4th state vector as well. And here also we will have x4 available to us, and so we run this system, and now you can see that your state x1, which is in the blue color, it goes exactly to the value 3, which is the desirable value for the state x1, and this is the integrator state. All of this we have done in the previous lecture. This is just the repetition of that, in case it's been some time you listen to that lecture. So we can also change this value to, let's say, 10. Control S and see if it tracks 10 value. So you can see here that now x1 is tracking the constant value 10, and we can also change it to, let's say, -4, any constant value. Save this and run this. So now the x1 is tracking the value -4. So that's the integral control. And now we come to the point of today's lecture, that how do we incorporate the state observer in this integral control. So notice that the original system that we had was a 3 by 3 system. So we need, let us suppose that the output that we have is x1. So we are measuring x1 using the sensors, and if the output is x1, then we have to estimate the remaining 2 states, x2 and x3, using the Leuenberger observer. And you already know that the dynamics of the Leuenberger observer, if I add the dynamics of the Leuenberger observer will have 3 states of its own, and those will be the estimates of x1, x2, x3. x4, which is the integral state, that will stay out of the observer dynamics. So what we do is, first of all, we calculate the observer gain using the old 3 by 3 A and B matrix. So this is the 3 by 3 original A matrix without the integrator state. And let us suppose my output C is equal to 1 0 0, which means that I am measuring the first state x1 only. And now I have already checked the observability of these matrices. You can see here that I have checked it here, but I can also check using MATLAB as well. So for example, I can check by using the command rank of C into A and C into A into A. So this is CA square. So the rank is 3, which means that this O matrix is full rank, and because the system is of third order, so 3 is full rank. So now I can use the place command. Let's suppose I place the eigenvalues of the observer at -1, -2 and -3, and I use A transpose and C transpose. Notice that this A is now the 3 by 3 matrix. I have defined it, and this I call this observer gain L. So the same command that is used to calculate the controller gain can be used to calculate the observer gain, and the observer gain will be 4, 6 and 2, but this will be a column vector, not a row vector. So 4, 6 and 2, I place this L equal 4, 6 and 2, and now this is the observer gain. Now what I do is simply in this case, now the control will be using the estimate of the state, not the state themselves. So it will be using the state number 5, 6 and 7. State number 5, 6 and 7 are the estimates of state number 1, 2 and 3, which are the original states of the system. And we shall define dx2 here, which is A times x plus B times U plus L times the output and the estimate of the output. In our case, output is x1 minus the estimate of the output is x5. So that will be dx2. So dx will be equal to the dx1 semicolon dx2, which is the column vector of 7 cross 1 with 7 states, 3 original states, 3 state estimates and 1 integrator state. But here in the dynamics of the observer, you have to use the 3 by 3 form of A matrix. So 1 to 3 comma 1 to 3. That means that I am using the first 3 rows and first 3 columns of this 4 by 4 A matrix. This A matrix is 4 by 4, so I am using only the 3 by 3 part of this A matrix for observer dynamics. And the states in the observer dynamics are state number 5, 6 and 7. Similarly, the B matrix in observer dynamics is 1 to 3, 1 to 3, and then L multiply by x1 minus x5. So those are the observer dynamics. Alright, so now we have defined the observer dynamics here, and next we save this file and we go to this file, and now we have to provide the initial conditions for observer states as well. So we provide 0 initial conditions for observer states, and we say this is x1 hat and this is x2 hat, and then the seventh state is x3 hat. You can use any x3 E, or you can use anything to represent the estimation. Okay, so we have run into some error. So inner dimensions do not agree. So okay, so here I have used the 3 states, but the controller gain has been calculated using 4 states. So we have to add the integrator state as it is x4. So remember that without the observer we used x1, x2, x3 and x4 as the states that contribute to the control law. Now x1, x2, x3 have been replaced by their estimate generated by the observer, but x4 remains as it is, because x4 is our calculated state. It is not the state of the system. It is something that we have introduced as a way of doing calculations. So we run this and we still have an error here. So we go back and we see that there is a problem. Yes, why not? Because we have here x1 to 4. So first 4 states come into this part of the system. We save it and hopefully all the errors are removed now, and yes. So now you can see here that the blue line is state x1 and this magenta line is the estimate of x1. So you can see that x1 and its estimate start with different initial conditions, and x1 estimate converges to the x1. Not only that, the state estimate converges to the actual state value, which means that our observer is working fine, but also our state converges to the desirable value. So this is the output state of the system. So output goes to the desirable value, which I can show you here that with this is -4 here. So I go back to the figure. So output goes to the desirable value, rest of the system is asymptotically stable. This green line is x2 and yellow line is the estimate of x2. You can see here that the estimate of x2 converges to the actual value of x2, and similarly this red line is x3 and this black line is the estimate of x3. So they also converge, the estimate is converging to the actual value, and this is the integrator state which is doing this job of removing steady state error. So now with this lecture you have learned how to implement feedback control dynamic compensator using the observer with the integral control as well. So this completes our series of lectures on integral control, observer based control and the observer based integral control. Hopefully these lectures are useful for you. Please do refer to my lectures on theory, where I have a theoretical lecture on how to design state feedback control and how to design state observer based dynamic compensator, state estimation based state feedback control. So if you combine theory with this simulation, that will give you a complete sense of what control systems engineering is all about. The third part, the only part that remains beyond this point, is practical implementation with microcontrollers and the hardware. So far I don't have enough resources to create videos for those, but hopefully these videos of simulations and theoretical the results will help you get a good insight into the control systems theory. Thank you for watching. Please let me know if you have any questions.